Hello everyone, welcome to this 10th lecture of Mineralogy in this Mineralogy lecture series. And in today's lecture, I will mostly talk about analytical technique which is widely used in mineralogy. There are two techniques which I will discuss in this lecture or in the next lecture, and that is about the X-ray diffraction technique and electron probe microanalyzer technique. In the first technique, which is the X-ray diffraction technique, in that one we basically try to measure the crystal structure of any crystalline material. So, it is very useful to know the crystal structure, and because sometime what happens that you do not have a very big crystals and you have a very tiny crystal and you cannot see the morphology of the crystal. So, if you have a big crystal, you can easily identify by looking at the shape and from the morphology. But suppose in the rock you have a very tiny material or very tiny mineral which is very difficult to identify. So, in that case we use a X-ray diffractometer. So, in this technique, first I will quickly discuss about what is X-rays, because X-ray is electromagnetic radiation, and because it is radiation, so it has a certain energy. And if you see this diagram, so X-ray comes in this range. So, X-ray comes in this range, and so they have a frequency larger than the ultraviolet radiation and lower than the gamma radiation. And also if you see that their wavelength, so they are very short in wavelength, and because of that they have a very high energy, and because of that this property makes them very unique, which is very helpful to determine the crystal structure of any crystalline material. So, if you see the wavelength, so the wavelength of your X-ray is between 0.01 angstrom to 100 angstrom, and because it has the energy directly proportional to your frequency. So, you can also write down E is equal to h mu, and where mu is your frequency, or you can also write down h c by lambda, where h is your Planck constant and c is your speed of light and lambda is your wavelength. So, if you consider that this electromagnetic radiation which comes in the X-ray region and have a wavelength of lambda is equal to 1 angstrom, and if you try to calculate the energy of this particular radiation, this electromagnetic radiation, so that will be very close to your 12,400 electron volt. So, if you see the energy of the X-ray which has a wavelength of 1 angstrom, and the energy is 12,400 electron volt, and if you compare with the ionization energy of any element, and basically ionization energy is the energy which holds the outer shell electron to the nucleus. So, if you see for example, if you see the hydrogen, so hydrogen has ionization energy in the outer shell is equal to almost a 14 electron volt, and if you see any natural occurring element and if you see the ionization energy, so that will be not more than your hardly 2000 electron volt, or most of the element even have a less than 1000 electron volt. So, compared to that, this energy of this X-ray is very high, and because of that they can remove any of the electrons which are present in the different shells in the atom. They can easily remove, because ionization energy is much lesser than the energy of the X-ray. So, because of that they produce a certain kind of characteristic peak and photon, and that is very characteristic for the material. To understand this, first we quickly try to go to this history of X-ray. So, X-ray was discovered by Professor Wilhelm C. Röntgen. So, this is a picture of Professor Röntgen. He was a professor in University of Würzburg, which is situated in Bavaria in Germany. So, he was a professor there, and he was mostly interested in gas discharge tube, and his interest was to work on a high voltage and low pressure. So, he was working in a gas discharge tube, and he was trying to connect the gas discharge tube with a high voltage and low pressure and try to see what kind of effect it will have. So, for the discovery of X-rays, he received a Nobel Prize in 1901 for his contribution in physics, and he was the first recipient of Nobel Prize. And if you see, there are two other interesting images. The first image of this left hand side, this image is the first X-ray of a part of human body. You can see there is a bone of the fingers, and you can see there is some black portion is here. This is basically a hand of his wife, and this is her marriage ring. So, this is the first X-ray radiograph of a human body that was taken by Professor Roentgen, and this is his lab where he discovered this mysterious rays in 1895. So, if you see his experiment, so this is the experiment, and this experiment contains there was a Crookes apparatus. This is a Crookes apparatus, like a funnel shape apparatus. So, that apparatus is connected with some electric supply. So, basically some voltage was generated in this Crookes apparatus. So, basically Crookes apparatus, if you simplify this drawing, so it will look like this, and so basically in this apparatus, in this Crookes apparatus, which is called as a gas discharge tube. So, because he was interested in low pressure and high voltage, so he removed most of the air that was present inside this gas discharge tube. So, the gas discharge tube was made up of a glass tube, okay, and he removed all the air from which is present inside this gas discharge tube, and there was a cathode. So, there was a cathode, and there was a cathode and there was a anode, and this cathode and anode was connected with a series of battery and with some inductor, or you can say some choke point, and so because of that there was some kind of potential difference in this connection. So, when he was trying to do his experiment at a very low pressure, what he observed when he was connected this supply with a series of batteries and with an inductor. So, there was some kind of potential difference. So, that is V 0, and this V 0 is basically producing some of the electrons in this cathode plate, and this electron, because there is a vacuum inside this gas discharge tube. So, because there was some kind of potential difference. So, if you see the work done by this electron is before it accelerate. So, basically if there is there was a vacuum inside this gas discharge tube. So, this electron was accelerating towards the anode, because it has a positive charge and it has a negative charge. So, when you try to calculate how much work done by this electron before reaching the anode, if you see the work done by this electron, so that will be equal to the charge multiplied by the potential difference, and that is your V 0. So, basically your work done is, if the charge is E, So, EV naught. Okay. So, this is the work done by the electron before striking the anode, because it has a certain velocity also. So, if we suppose this electron has a velocity v, so you can calculate the kinetic energy. So, basically your work done by this electron will be EV0, and that will be equal to your kinetic energy. And if this electron has a velocity v, so you can also write down this is half mv square is equal to EV naught. So, this is the work done and kinetic energy of the electron, which is generated at the cathode by the potential difference V0, and it has a velocity of v. Okay. So, once when this Roentgen, he was performing an experiment. So, one day during an experiment, what he observed, that when he supply a voltage to this gas discharge tube, so what happens, that there was some photographic plate in front of this Crookes apparatus, or in front of the gas discharge tube, and basically he painted the front of this photographic plate with barium platinum cyanide. So, when he painted the barium platinum cyanide, one day when he was performing his experiment, he discovered that there was some kind of glowing in this photographic plate. So, he immediately thought that is there any effect of a light to this photographic plate or not. So, what he did, he immediately cover this gas discharge tube with a opaque black solid wood. So, when he covered this gas discharge tube with a solid wood box, so still he can see that his photographic plate, which was painted with a barium platinum cyanide, is still glowing. So, he understand that this is basically not a radiation which is coming from the light region. So, basically this is a radiation, but this has some other kind of radiation. So, what he did, he immediately turned off the voltage, or turn off the voltage of this circuit. When he turned off the voltage, what he observed, that there was no glowing in this photographic plate. Okay. Then again, when he turned on the voltage, he realized that there is again a glowing in the photographic plate. So, then he thought maybe he should put some material in between, and he placed one piece of paper in between in between the gas discharge tube and the photographic plate. But the radiation which was generated by this gas discharge tube, that was coming out from completely from this paper, and there was no shadow in the photographic plate. Then he thought, let's put some heavy material or dense material. So, he put some metal foil in between the gas discharge tube and the photographic plate. But once he placed some heavy material, he can see some kind of shadow of that heavy material in the photographic plate. So, he understand that these radiations which are generating from this gas discharge tube is basically can easily penetrate the lighter material, but when he placed a heavier material, this radiation could not penetrate the heavier material. Then the third thing what he did, he placed his hand. When he placed his hand, he can see some kind of shadow of his bone, but the soft tissues he can't see in this image. So, he realized that the soft tissues, this radiation can easily penetrate the soft tissue of his hand, but not the denser bones. So, from that he realized that this radiation is something new, and that time many people were thinking that there should be some kind of effect of the voltage in the gas discharge tube. So, then because it was a very mysterious kind of radiation and X denotes denotes the mystery. So, that is why he called this radiation as a X-ray. So, he called this radiation as a X-ray. So, in this way X-ray was discovered in 1995, and the second thought he gave on this discovery is that when you have an electron and that electron is accelerating at the velocity of v, and when this electron is striking the anode, so there should be some kind of interaction of electron with this anode, and anode is mostly made up of metals. So, to understand this, we should try to understand the energy level diagram of the anode. So, if you see the energy level diagram of any metal, so it has a different energy levels. So, for example, it is not in scale, but suppose it has a E1 energy, it has a E2 energy, it has a E3 energy, it has a E4 energy. So, if this is energy of the K shell, this is the energy of the M shell, L shell, this is the energy of the M shell, and this is the energy of the N shell. And similarly, you have some other energy, and there is infinite. So, suppose you have an incident electron, and this incident electron has a velocity v, and this electron is moving and striking your anode, which is a metal, and this is a lowest energy. E1 is the lowest energy, and E4 is the, suppose in this case, highest energy. So, when this electron, this incident electron, which has a E charge and potential difference is V0, and it has a kinetic energy of half mv square. So, when this energy, if you see the energy of this incident electron, which is in a thousandth of electron volt. So, when it will strike the K shell, so in the K shell you have some electron, 2 electrons. So, because the binding energy or the ionization energy of the electron which is present in the K shell is much lower than the energy of the X-ray. So, what this X-ray will do? It will remove the inner shell electron from the K shell, and it will put this electron to the infinity. So, when it will put the electron in the infinity, there will be a void in the K shell. When there will be a void in the K shell, so what will happen? That there is a vacancy here, and the electron which are present in the higher energy level in the L, M and N shell. So, what they will try to do? The electron which is present in the L shell will try to jump to the lower energy level for the stability. So, when the electron will jump from the L shell to the K shell, so because the electron which was present in the L shell has a higher energy. So, when it will jump to the K shell, there will be some energy difference when L shell electron will jump to the K shell. So, this energy, this difference will be removed in the form of photon, and this will be h nu, okay, and this particular photon will called as a k alpha. So, basically when your electron will move from the higher energy level configuration to the lower energy configuration, there will be some emission of photon, and this photon will have a k alpha this energy. So, and this will called as a k alpha, and this is a characteristic for a particular material. There will be another possibility that this void space can be filled by the electron which is present in the M shell. So, in that case there will be again some kind of emission, or there will be some kind of release of a photon, and because the electron which is present in the much higher level in the M shell, they are coming to the K shell. So, there will be another type of characteristic this X-ray will produce, that is called as a K beta. So, basically when from the higher level energy level to the lower level energy level, this electrons will jump. So, it depends on what is the final destination. So, because in the first two cases your electron is moving from the L and M shell to the K shell. So, we always have a K alpha or K beta. So, when it will jump from the L to or from the second to the first level, so we use a alpha, and when it will come from the third to the first, we will use a beta. In case of the M shell, suppose if there is a vacancy in the K shell, and if it will jump from N shell to the K shell, because their final destination is K. So, there will be some excess energy that will release in the form of photon, because they are coming to the K shell. So, it will be a K gamma. Okay. Similarly, this electron, incident electron, will hit the L shell, also the M shell and the N shell. So, let us take an example of the L shell. When it will strike the L shell, so it will remove some of the electrons from the L shell, and there will be a void in the L shell, and because of this void, higher energy level electrons will try to come to the lower energy level, and when it will come to the lower energy, it will produce because they are coming to the L shell. So, they will produce L, and they are coming from the M to L. So, it will produce L alpha. If they come from N to L, it will produce a L beta. So, in this way you can get many different types of characteristic these peaks, and these characteristic peaks will be particular for particular material. So, if you use a copper or molybdenum or any other metal or any other element, so they have a characteristic K alpha and K beta. So, this is the first thing. And if you see the typical this X-ray. So, this X-ray has two different things in this diagram. So, this is the x axis is a wavelength, and your y axis is your X-ray intensity. So, if you see this diagram, so basically it has two parts. Okay. So, if you have suppose certain wavelength of any X-ray. So, if you try to calculate the wavelength, that is a sigma naught. So, if you take this one, so that is equal to h c by E, and you can that will be equal to h c by E v 0, where E is the charge of the electron and V 0 is the potential difference. Okay. So, if you try to calculate the minimum value of your lambda, the minimum value of the wavelength of the photon. Okay. So, that will be equal to when you have a maximum this V 0. Okay. So, if you have E v naught, that is a maximum, because energy is inversely proportional to lambda. So, when you have a maximum energy, in that case you have a minimum this lambda value for particular incident this electron. If you try to calculate the maximum wavelength of the photon, so that will be equal to h c by when your E is almost equal to 0. So, it will have some energy, but it will very close to 0. So, in that case your this lambda max will be equal to infinity. Okay. So, that will be equal to infinity, and so if you try to plot the graph, if you try to plot a graph, and if you take your wavelength, so lambda, and lambda is increasing in this direction, and if you take number of photons that are producing by the by the interaction of the incident electron with the material. So, that is the number of photons that is equal to the intensity, because intensity is proportional to the number of photon. So, basically what will happen, that when your electron will interact, incident electron will interact with your atom. So, it has a two parts. The first part, that it will interact with a K, L and M shell electron. So, K, L, M, N shell electron, and also it will interact with your nucleus. Okay. So, when it will suppose if you have an atom and there are some atoms, and when there is a, let us erase this part. So, suppose if you have, let us think that we have an atom and we are just ignoring the electron part, we are just taking the center part of the atom, because in the atom your 99.9% space is empty. So, only the nucleus have some mass. So, basically when the X-ray is coming, okay, towards the nucleus, so what will happen, that it will come in this velocity and force will be perpendicular to this one. So, there will be some kind of deflection. Okay. When it will be close to this one, okay, there will be more deflection. Similarly, if the electron or if the X-ray will strike the nucleus at the center of the nucleus. So, all the kinetic energy produced by the X-ray will convert to the photon energy, and there will be some kind of breakage here. So, in that case we use a term which is a Brahms So, we use the term this Brahms trailing. So, Brahms means brake. So, like we apply a brake to our vehicle, and there is a brake in the race. So, basically this is a German word. So, this is a brake in the race. So, we convert all the kinetic energy to your photon energy. So, basically when you try to supply a certain current to this your gas discharge tube. So, what gas discharge tube will do, because you are supplying a current, so current will produce a number of electrons. So, if you increase the current, what will happen, the number of electrons which are producing it at the cathode, when you increase the current. So, initially you will have so basically when you increase the current in the gas discharge tube, so your number of electron produced at the cathode will also increase, and when it will produce a more number of electron, it will accelerate toward the anode. Okay. So, if you see the this lambda 0, so lambda minimum, so the lambda minimum has a value of very close to 0, or it has a minimum value. So, suppose if it has some value, and similarly you have a different value, different photons which has a different wavelength. So, you have a series of wavelength for the photons for particular material, and at particular maximum lambda value you will have a infinity, at infinity you have a wavelength maximum. So, your graph will look something like this. Okay. And this one is called as a continuous X-ray. Or continuous radiation. Okay. When you try to increase the current, okay, at a constant V0, okay, what will happen, that you will produce a more number of electrons. So, basically your this graph will basically move to the, because you are producing a number of more electrons. So, it will produce a number of more photons and your graph will move in the upper direction. But if you change the voltage as shown in this left hand side diagram. So, if you see the initially your graph when you have a certain voltage. So, suppose at 5 kilovolt this voltage, your graph, your continuous peak will look like this. So, this is your lambda minimum, and at some infinite you will have a lambda maximum. So, when you increase the voltage, so if you see this relation, so basically your lambda naught is inversely proportional to V 0. So, when you increase the V 0, so automatically your lambda naught value or lambda minimum value will decrease. So, when you increase the voltage, your this value is moving in this direction. So, you will get a lambda minimum value at a lower number. So, when you increase the voltage, your lambda minimum value is moving in this direction and you get a lower lambda minimum value. After a certain voltage, what will happen, that when your this X-ray or the incident electron will interact with a K, L and M shell. So, what will happen, that at particular lambda value, at particular wavelength, you get a some kind of a characteristic K alpha or K beta value. Okay. So, basically at a particular wavelength, you get a K alpha, K beta, L alpha, L beta value. Okay. So, basically when you increase the voltage at after certain voltage, when there will be some interaction of the X-rays with some interaction of incident electron with a K, L, M shell electron, they will try to eject that electron, dislodge the electron, and the higher shell electron will try to come to the lower shell electron and it will produce some characteristic X-rays. And if you see this diagram, what you will observe, that your this K alpha has a lower energy than the K beta, but K alpha has a higher energy than the L alpha. So, your energy is increasing in this direction because it is inversely proportional to your this alpha. So, basically if you see the energy level diagram, energy level diagram. So, when your K alpha and this is a K beta, this is your L alpha, this is your L beta. So, when you have this K alpha, okay, so K alpha, because it has a highest energy, because if you see that if you see the K alpha, it has a higher energy than the L alpha, because the energy to put a electron from the L shell to the K shell, you need a higher energy than the energy is required to put from the M shell to the L shell. Okay. So, that is why your K alpha is higher than the L alpha. But if you see the K alpha with a K beta, because K beta is producing when the electron is moving from the M shell to the K shell. So, in that case your K beta will have a higher energy. Okay. If you see the intensity, so intensity of your K alpha is always greater than the intensity of K beta, because if you see the energy which is present in this electron in the L shell, they can come several times to the K shell, but the electron which is present in the M shell, they can come only few times. So, basically the intensity of the K beta will be always lower. So, if you see the intensity, so intensity is always K beta will be lower than the K alpha. So, similarly the L beta intensity will be always lower than the L alpha. Okay. So, this is about the continuous radiation, and these are your characteristic radiation. Characteristic radiation or characteristics X-rays. Okay. So, if you try to see the application of the X-rays, so there are two laws or there are two methods which are widely used. The first method is your Bragg's law. So, in the Bragg's law, this is a photograph of Professor William Bragg and Lawrence Bragg, and they are father and son. So, they received the Nobel Prize in 1915 for their contribution to in X-rays, in the field of X-rays. So, what they suggest that if you have a crystal, so in this crystals you have a different planes, different HKL planes, and in this HKL planes you have a different atoms. So, suppose if there is a X-ray 1 is coming towards the crystalline material, and if this is a flat, if the surface, top surface is flat. So, if you take all the planes as a flat surface, mirror plane. So, your this X-ray which has some wavelength, and this will strike the atom which is present at the particular HKL plane and at the angle of theta, and that will reflect, because this is a flat mirror plane. So, this will reflect at a theta angle, and your this incident, this X-ray will be equal to the reflection of the X-ray. So, that will be also a theta. So, if there is another plane and there is a second X-ray which has exactly the same wavelength, and if that strike the atom in the next this plane. So, what will happen that the second X-ray which is travelling, which is striking at a similar theta angle and reflected at a theta angle. So, in that case what will happen that if you mark this one as a and this one, if you draw a perpendicular from the point A to this ray 2. So, there is a perpendicular, this one and this one is a perpendicular. So, this is a 90 degree. So, if you basically draw a perpendicular from point A, and if you mark this one as a B point, this is a C point and this is a D point. So, basically if this ray 2 which is striking a point C is basically travelling a extra distance compared to the X-ray 1. So, if you see the extra distance travelled by a ray 2, that is equal to B C plus C D, and if both X-rays have a similar wavelength, and if in the first situation the crest of the X-ray 1 and the crest of the X-ray 1 is exactly at the same position, and the trough is exactly at the same position of these two X-rays. So, in that case what will happen? You will have a constructive interference, and when there will be a constructive interference, you will have a amplification of the two, these X-rays will merge and it will have some kind of amplification. Okay. So, in that case if you try to solve it with a trigonometry. So, this your B C plus N D B C plus C D will be equal to 2 D sin theta, where your D is a interplanar distance. So, this distance is your basically a D between the two planes. So, if you solve this one, this will equal to the n lambda, and by this way Bragg's introduced this formula, and from this method they basically determine the crystal structure of salt, of halite. So, if you have a constructive interference, your n will be always a integer number, that will be 1, 2, 3, 4, some integer number. If you have a suppose another planes in between these two planes, and there will be another third X-ray which is exactly the same. So, when this will strike, this particular point, it will reflect, and it also has a theta, this incident angle, and theta, this reflected angle. So, in this case, when you have some intermolecular atom in between these two planes, so what will happen, that your this n will be always 1 by 2, it will be not be integer value. So, in that case, your basically lambda will be half equal to 2 d sin theta, and in this case basically your this particular crest will be matching with a turf of the ray 3, and in that case if you compare ray 1 and ray 3 or ray 3 with a ray 2. So, there this crest will not matching with a crest, it will matching with a trough. So, in that case you will have a destructive interference and you will not get any signal. So, you will get a completely a flat line. So, when your n is not an integer value, so you will not get any reflection. So, that was a very simple principle which was derived by the William and Lawrence Bragg, and we basically apply this Bragg's law to measure the crystal structure of a crystalline material. And what we do, we basically make a powder sample. So, we take a powder sample, and what we do, we put the powder sample. So, this is the X-ray diffraction XRD, and this has a 3 different part. The first part is your X-ray source. So, you have a X-ray source which is present here. So, basically it will produce some X-ray, and in this particular X-ray diffractometer, in this one, we basically use a fixed lambda value. So, we basically use a monochromatic X-rays, monochromatic X-ray. So, monochromatic X-ray means that we have a single wavelength. So, lambda is fixed. Okay. And what we do, we basically change the theta. So, theta will be vary. Okay. So, we have a first part where the X-ray is produced, and this X-ray has a fixed value. For example, if we are using copper, so copper has a particular X-ray value. So, we can fix the X-ray value. Okay. And then the second part we have a sample chamber or sample holder. So, we have some kind of glass material, and in this glass material we put all the powder of the powder sample. So, this is present here. Okay. And then we have a third part which is a detector, and detector is present somewhere here. So, basically your incident X-ray is coming, it is striking the powder sample, and when there will be a continuous interference. So, you will get a reflection, and that will be detected by the detector, and during the analysis we change this 2 theta. Okay. So, we change this 2 theta, and at different 2 theta value, because there are different planes which are present in your crystal, because this is a powder sample. So, basically your different planes will be randomly oriented, and this will at particular theta value, when there will be a continuous interference. So, there will be some kind of reflection. So, this is a very useful method by which very easily we can get a idea about the crystal structure of a unknown material, but the only drawback is that because we need a powder sample. So, you should have a sample which is relatively bigger in size. If you have a very tiny sample, you cannot make a powder of this sample. So, in that case you are not able to use this X-ray diffraction method. So, you need a powder sample at least a gram of material. Okay. So, basically you get this type of diagram, and in the particular 2 theta value you see there is a reflection. There is a reflection of at this value, there is a reflection at this value, and there is a reflection at this value. So, you for the this is a X-ray for the halide, and at particular 2 theta you get a different this intensity of different HKL plane. And now we have a very large data set. So, automatically program can calculate that what would be the 2 theta, what would be the HKL value for particular 2 theta. But initially when Bragg and other people were started this kind of experiment, they did not know the particular 2 theta value have a particular HKL for particular material. So, they have to calculate that, and to calculate that we need some kind of a selection rule. And if you use this one for the cubic crystal, so in cubic crystal we know that there are 14 different types of HKL plane, and these are the different 14 this HKL plane for the cubic system starting from 100, 110, 111. So, there are different HKL plane for the cubic system. And if you take a sum of the square of the HKL, for example, because it has a 100, so 1 square plus 0 square plus 0 square, that will be 1. So, this will be the value of the your sum of the H square plus K square plus L square. If you see the reflection in the simple cubic system, SC means the simple cubic system. So, there will be a reflection of all the 14 planes for the simple cubic system. If you see the BCC body centered cubic crystal structure, so body centered cubic crystal structure will give a reflection at a particular HKL value. Okay. And if you see the sum of the HKL, for example, if you see the reflection, okay. So, when the sum of the square is always you have a even number. So, if you see there will be a reflection at 2, there is a reflection of 4, there is a reflection of 6, there will be a reflection of 10, there will be a reflection of 12, there will be a reflection of 14 and 16. So, when your H plus K plus L, this will give you a even number. So, in that case you have always a reflection for a BCC structure. Okay. So, BCC will give a reflection in only those planes which has a sum of the HKL plane is a even number. Okay. In case of FCC, that is a face centered cubic crystal structure. So, in case of face centered cubic crystal structure, you will get a reflection if all the HKL either is a odd or even number. Okay. For example, if you see the reflection of the face centered cubic crystal, so the first reflection will be given by this your 111 plane, because 111 all these 3 are odd number. So, there will be a reflection. If you see the next reflection, the next reflection for the FCC plane will be for 200 plane, and 200 plane 0 is considered as a even number. So, 2 is a even number, 0 is a even, and then again 0 is a even. So, all this HKL is a even number. So, you have a reflection. If you see the next one, so next one is a 220. So, 220, 2 is a even, 2 is a even, 0 is a even. So, all the HKL is even. So, you will have a reflection. If you see in between, so 1 is a odd, 0 is a even, 0 is a even. So, it is a mixed kind of HKL. So, there is a no reflection. Similarly, 110, 1 is a odd, 1 is a odd and 0 is a even. So, there is a no reflection. So, this is some kind of reflection rule for the simple cubic system and BCC and FCC crystal structure. So, if you see the simple cubic, you will get reflection when your HKL will be H square plus K square plus L will be 1, 2, 3, 4, 5, 6, 8, 9, 10, 11 and so on. Similarly, for the BCC, you have a reflection for 2, 4, 6, 8, 10, 12, 14, 16. So, if you compare with a simple cubic with a VCC, what you will observe if you go directly to the 7th peak. Okay. So, 7th peak either you are getting a 14 or 7, and here in the 7th peak you are getting a value of 8. So, if you see the 1, 2, 3, 4, 5, 6, here also you are getting 2, 4, 6, 8, 10, 12. So, these are exactly the same. This is just a multiplication by 2, but if you see the 7th peak, here you are getting either 8 or here you are getting a 7 or 14. So, to distinguish the simple cubic with a BCC, you should directly go to the 7th peak. In case of your FCC, crystal, in case of FCC, you see you get a reflection for 3, 4, then you get a reflection for 8, then you get a reflection for 11, then you get a reflection for 12, then you get a reflection for 16. So, in case of FCC, it is relatively simple. So, let us try to calculate the crystal structure of some unknown material. So, this is suppose you get a 2 theta value, and at these 2 theta value you get a reflection, and you do not know what would be the HKL value at that particular 2 theta value. Okay. So, what we have to do, first we have to calculate the sine square theta. So, we will calculate the sine square theta, and sine square theta for this 2 theta value is given here. Okay. And then the next step is we have to normalize this. How we can normalize? If we divide this first cell with a 0.143, and similarly all the rows will be divided by 0.143. So, if you divide this by the first value, so you will normalize, and this normalize will give you 1.00 value for the 2 theta value of 44.48, for 51.83 it will give you a value of 1.34 and so on. Now, the third step is we have to make a clear fraction, because from this one you cannot basically predict the HKL value, because this is not an integer value. So, we should have a some integer value, and integer value we will get using this clear fraction, or by make a clear fraction of this normalized value. So, suppose if you compare the first two normalized value. So, you see that this one, if you take this 1 and 1.34, so this is 4 times of this first clear value. So, if you divide this with a 0.33, so if you divide every number by 0.33, so you more or less you will get a clear fraction or integer value. So, if you see here, if you make a clear fraction from this normalized value, so you get a 3, 4, 8, 11 and 12, 16, 19 and 20. Okay. And now, you have to try to calculate for this integer value or for this clear fraction value, what are the possibility of different HKL, where your h square plus k square plus l square should have this clear fraction value. Okay. So, in case of your 3, if you see this 3, so basically for this h square plus k square plus l square, you have only one option, that is a 1 1 1. Similarly, for the 4, you will have this HKL value for 2 0 0. You can also say that this can also possible 0 2 0 or 0 0 2. Of course, it is possible, because 2 0 0, 0 2 0 and 0 0 2 all are the parallel to the or they have a similar this HKL value. So, you can put anything, but you cannot confirm that it will be a 2 0 0, it can be 0 2 0 or 0 0 2. So, let us say it is a 2 0 0. Similarly, for this clear fraction of it, the HKL value will be 2 2 0. So, from this h square plus k square plus l square, you basically can calculate, you can predict that, because the h square plus k square plus L square is getting a reflection at 3, 4, 8, 11, 12, 16. So, this is a FCC crystal structure. So, this material has a FCC crystal structure, and also you can calculate the few other things. So, I will not go in that, but this is just a very simple explanation that how the Braggs and other they try to calculate the HKL value when you have a 2 theta value. So, in case of your unknown substance, when you get a reflection at the 2 theta value, so what you can do, you can easily check that if suppose you have a quartz. So, you should see that the quartz give a reflection at close to this 2 theta value, and you should also see the intensity. So, from the archive you should try to see that maximum intensity will be given for the which 2 theta value, and if your unknown sample gives the maximum intensity close to that 2 theta value. So, in that case your material is whatever archive you are using. So, it could be a quartz or whatever material you have. So, by this way you can easily calculate the HKL value, and there is a second type of a method which is also used in the mineralogy in earth sciences, that is the Lave method. And Lave method is very useful when you have a single crystal and your material is tiny. So, basically this Lave method, this is a photograph of Professor Max von Laue, and he was a German physicist, and for his contribution in the field of X-rays, he received a Nobel Prize just 1 year before the Braggs, this father and son duo, and he was working on the X-rays, and his approach was slightly different. So, what he said that when you have a different atoms present in the plane, so if there is a X-ray and these X-ray will strike the different atom. So, there will be some kind of scattering, and this scattering, if these two X-rays are there, if in somewhere if there is interference, so there will be if there is a continuous interference. So, in that case you will have some kind of reflection. So, basically in this Laue technique, where you use a white X-ray, we use a white X-ray. So, basically lambda is vary. So, you do not use a fixed lambda value, but your theta is always fixed. So, when the X-ray which has a wide range of lambda value, when it strikes the unknown material, this sample crystal, so when it will, there will be an interference, there will be a scattering. So, it will give us some spot pattern, there will be some spot pattern, and this spot pattern is very useful for predicting the symmetry elements in your crystal structure. So, from the Laue method you can determine the symmetry of the material, but you can't say that what kind of crystal structure it has. So, you can only predict about the symmetry element. So, for example, if your material has this kind of pattern, this kind of spot pattern in the Laue method. So, if you see that if you rotate this pattern, so if you rotate by 45 degree, so you will not find the exact pattern. So, if you rotate it by 90 degrees, so you cannot distinguish that it is rotated. So, if you rotate by 90 degrees, so this particular pattern will give you a 4-fold symmetry. So, means at this particular plane it has a 4-fold symmetry. Similarly, if your pattern is something like this. So, in this, if you try to rotate it and you get exactly the same pattern, so you have to rotate it for 180 degrees. So, when you rotate it for 180 degree, you get a 2-fold symmetry. So, basically from this spot pattern, for the single crystal, you can predict that what is the symmetry element in this unknown material, and then you should check the archive that if you have a this symmetry element, so what would be the best fit. So, in this way you can determine the crystal structure from the symmetry element. So, there is a two different method which is widely used earth science, that is a Bragg's method, and second one is a Laue technique. In the Bragg's method, we basically use a single wavelength, and we vary the theta, and in case of your Laue technique, we fix basically the theta, but we vary the lambda. So, we use a white X-ray. So, this is about the first analytical technique in the mineralogy which is used, and in the second part, in the next lecture, we will try to understand the electron probe microanalyzer, how it works, and we will try to cover one another topic in the next lecture. Thank you.